Okay, at this point we should be fairly comfortable with the idea of a derivative. The only problem is getting the answers. Um, we saw the limit definition, and that limit definition can be quite extensive when it comes to certain examples. We only looked at a couple of different examples. One's mainly that relate to polynomials, so linear, quadratic polynomials. Um, and so what we want to look at is to see that there seems to be a pattern to doing these derivatives, and there in fact is. And if we could narrow down on that pattern, we might be able to simplify the computation in finding the derivative. Now, it should still mean the same thing in that we're finding the slope of the graph or the slope of the tangent line or the derivative itself, but we're getting the answer a little bit quicker. And so we're going to come up with these rules per se, and they're basically going to be us applying the limit definition to functions that have a pattern to their derivatives. And so the first one we look at is the derivative of a constant. So we call this the constant rule. And it says if we're going to take the derivative of a constant, we should get 0 as an answer. So looking at this, we take the derivative of a constant, c representing a constant. The answer is 0. Applying that to, say, this example, here we have y equals 7. That is a constant function. If I wanted to find dy dx, which would be the derivative of y with respect to x, the answer should be 0 based off of what this says. Now, why does this say this? It didn't just appear. It has to do with the limit definition. So if we have a function f of x equals, say, a constant, what we would need for the limit definition is f of x plus delta x, which for a constant function would also just be c. And so if I want to take the derivative of this function, I would have to take the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Well, in this case, f of x plus delta x is c, f of x is c, all over delta x. Well, c minus c, anything minus itself, is going to be 0. And so I'm going to have the limit as delta x goes to 0 of 0 over delta x. Well, remember, delta x is going to 0, but isn't 0. It's going to 0. Well, if it's going to 0, 0 over something that's not 0 would always equal 0 as a whole. So ultimately, this is the limit as delta x goes to 0 of 0. Well, 0 is a constant. And we learned that limits of a constant are just that constant. And so the derivative for a constant function should equal 0. Now that's a long way of doing it. If you just remember that, anytime you take the derivative of just a constant, your answer is going to be 0. You can avoid doing all this every single time. And so that's the whole point of these rules we're going to start learning. We're going to try and come up with ways of taking derivatives of certain types of functions where we know what the answer will be after we're done through these simple patterns of applying the limit definition to these specific functions. So the next rule we want to learn is the power rule. So the power rule says if we're dealing with a power function is f of x equals x to the n, and the power that we're working with specifically, n, is a rational number. If you think of rational numbers that are written as fractions, then this is what the derivative of x to the n should look like. It should be n x to the n minus 1. So looking at this pattern, what you see is that the power for this function came out to the front, and the new power is 1 less than it was before. It's n minus 1. A couple of things here. You got to know what a rational number is. So the idea is that the real numbers are broken into two groups, rational and irrational. Okay? Rational numbers are numbers that can be written as a fraction, a over b. And so they would be positive, negative whole numbers, fractions themselves, finite decimals, infinite repeating decimals. They would all be rationals. Irrationals are numbers that can't be written as these fractions. And so these would be some common ones you should know would be something like pi, e, square root of 2, square root of 10, cube root of 29. I mean, these are all roots that can't be simplified anymore, but these are also common irrationals that you've learned before. These are all decimals that go on forever. They're infinite decimals that don't repeat, and they cannot be written in fractional form. So these are the exponents we cannot use power rule for yet. And it's mainly because of the proof behind why this works. But we'll get into that slightly in a second. I don't want to go too far into it. I really would prefer that we stick to just applying the rules, but we'll dive into it just a little bit. So anyway, first let's think about applying the rule. So here we have a function. F of x equals x to the fourth. X to the fourth is x to a rational number power. So the derivative, applying this power rule, should pull the power out to the front, and the new power should be 1 less. And that's simply the derivative. That was very quick, very easy, and there was no need for us to apply the limit definition because this is already applying the limit definition. We look at g of x. G of x I'm going to rewrite as x to the 2/3. That way it's x to a power. That power is a rational power. I'm going to take the derivative of this, and I'm going to get 2/3 x to the minus 1/3. Power came out to the front. The new power is 1 less than it was before. 2/3 minus 1 is negative 1/3. I will rewrite this as 2 over 3x to the 1/3 so that I don't have a negative exponent, but nonetheless that is your derivative. For the next function, I'm going to write this as y equals x to the negative 3 first. That's still just y, but I write it like that so that it is purely just x to a power. 1 over x to a power is not what this power rule applies to. The power rule only applies to taking the derivative of x to a power. So I need to rewrite this in that form, so that's this. Then I'm going to take the derivative, in which case I'm going to get negative 3x to the negative 4, simplifying negative 3 over x to the 4th. Finally, the last one, think of this as x to the first, right? This is always think of x as x to the first. So my derivative would be 1x to the 0. Remember, this exponent has to be 1 less than this. Well, x to the 0 should be 0, so this, or sorry, it should be 1. So I have 1 times 1, so I just get 1. So y prime is 1. So looking at this, power rule is pretty easy to apply now. It works for a couple of reasons. If I make some room here to show you why it works. It works because of the limit definition. And the idea is if we're doing this with the limit definition, we have a function, which is x to a power. We have to find f of x plus delta x, which would be x plus delta x to the n, in which case we would have to multiply this out. Now, if we multiply this out, we're going to get some long polynomial. That polynomial looks something like this, x to the n plus n, x to the n minus 1, delta x, plus, etc. It all depends on what this power is. We've seen what it was for x squared, for like a plus b squared, for a plus b cubed, etc. Pascal's triangle, binomial theorem, they're all ways of multiplying this out. Long story short, if we plug that into the derivative formula, the limit is delta x goes to 0 of x plus delta x to the n minus x to the n all over delta x. What we're going to see is that this thing, after we simplify it and cancel and take the limit as x goes to 0, ends up turning into nx to the n minus 1. It's no coincidence that you kind of see that sitting right here in some of the product that I multiplied out. For further investigation in something like this, you could easily take a look at the textbook. You could also search limit definition of the power rule, and you'll find infinitely many different videos out there that show you. At this point, I really would rather focus on applying the power rule other than sort of the proof behind it. But we could always take time and sit down and do that outside of class. Okay, so now we have this next one, which is find the slope of the graph. Well, in order to find the slope of the graph, you need to find the derivative. It just so happens that the function that we need to take the derivative of, that we want to find the slope of the graph of, is a power function. And so if we take the derivative of that power function using the power rule, we get 3x squared. If we want to find the slope of the graph, that's exactly the function that gives us the slope of the graph because it is the derivative. When we do it at -2, when x is -2, it's simply find the derivative at -2, which will give us 3 times -2 squared, which in this case will give us 12. So that is the slope of the graph, which is also the slope of the tangent line at x equals -2. This question is asking us to find the equation of the tangent line. Now, to find the equation of the tangent line is a little more involved than the previous question, in that we want to find the slope of the tangent line, and then use that to find the equation of the tangent line. Well, you should know how to find the equation of lines from algebra. If we have a point on that line, and we have a slope of that line, we could use the y minus y1 equals m times x minus x1 point slope formula. And so let's start off by using first the derivative. So we have our function f of x equals x squared. We have the derivative of that function to simply be 2x. Evaluating the derivative at -2 gives us 2 times -2, which is -4. Okay. And so what do we have? That is the slope of the tangent line at x equals -2. And so that's going to be the slope of this line that we're trying to write the equation of. The other thing we need is a point on that line. Well, that's when you have to start thinking about what's going on here. We have this parabola x squared. We have this x value of -2, which we locate onto the graph right there. That point on the graph, we said that the slope is -4. That's the slope of the graph because that's what the derivative gave us. But remember, that's the same as the slope of the tangent line to the graph at that point. It just so happens both of them share that specific point. Well, that point has a y value. The x value is -2. The way you could always find a y value is plugging into the original function. So if I found f of -2, here I found f prime of -2 and I got the slope. But if I find f of -2, that simply just gives me the y coordinate for this point where I found that slope. And so I'm going to get -2 squared, because that's the function, which is going to give me 4. So then really what I have is I have a slope of -4, and I have a point -2, 4, and I need to use this to find the equation of the line that has this slope and goes through this point, which is this line that we're talking about right here. Okay? Well, y minus 4 equals -4 times x plus 2 because this is a -2. So y minus 4 equals -4x minus 8. Move this 4 over, y equals -4x minus 4. This here is the equation of the tangent line to f of x equals x squared at -2, 4. Or I could also write that at x equals -2. Whether I just give the x value or I give the full point, doesn't really matter. Okay, we then build on top of that. So we have the derivative of a constant. We have the derivative of x to a power. We then have the constant multiple rule. Now the constant multiple rule, you have to understand how this really works. And it works similar to the scalar multiples rule that we had for limits. Scalar multiple, constant multiple, they're the same thing. And so the idea here is if we have some function that's differentiable that we can take the derivative of, and c is a real number, it's a constant, and we want to look at the derivative of this new function, which is c times f, then the idea here is if I want to take the derivative of c times f, since c is a constant multiple, c can be pulled outside of the derivative. We could just take the derivative of f and multiply c into whatever answer we get there. And so applying that to some of these examples, we see that this example, if rewritten as y equals 3x to the -2, can apply the constant multiple rule in addition to the power rule. So in taking the derivative, what I would do is I would take the derivative of 3x to the negative 2. But 3 is a constant multiple which can be pulled out. So I have 3 times the derivative of x to the negative 2. Well, 3 times that derivative, being negative 2x to the negative 3, would give me 3 times negative 2, which is negative 6. Drop that x to the negative 3 to the denominator, and that's the derivative, negative 6 over x cubed. Using this next one, again rewriting this as negative 3/5 times t, pulling that negative 3/5 out as a constant multiple. We see that f prime of t, if you pull that constant multiple out, really just requires you to take the derivative with respect to t of t, and you get negative 3/5 times 1, which would give you negative 3/5. So there's your derivative. And one last one, again, rewrite this. I'm going to take this negative 1/2, pull this out as a constant multiple. This I'm going to write as a fractional exponent and also bring to the numerator. So I'm going to write this as negative 3/4. 3/4 because of the third power and fourth root, but negative because I bring it up to the numerator. Now that's the function I'm going to take the derivative of. That's not the derivative. That is the function still. So then y prime would allow me to take the negative 1/2 and pull it out. Really only take the derivative of x to the negative 3/4, in which case that's just a power rule integral, so I get negative 1/2 times negative 3/4 x to the negative 7/4. New power is 1 less than the original, and here's the original power. Multiply this out, negative gives you positive, 3 over 8. Bring that x to the denominator because the negative x1 is 7/4, and there's my derivative. So then we have the sum and difference rule. Now in the sum and difference rule, if we pile that on top of the constant rule, the power rule, and the constant multiple rule, this will allow us to essentially take the derivative of polynomial functions, or functions that work very similarly to polynomial functions. And so what this says is that if I have two functions, f and g, and they're differentiable, which means I could take the derivative of it, and I want to take the sum or difference of those functions. So now I have f of x plus g of x, or f of x minus g of x, and I want to take the derivative of this whole thing. What I can do is I can take the derivative of each one separately and then add or subtract their answers together. So it allows you to split this apart, not have to take the derivative of all this at once, but take the derivative of each individual piece of the sum or difference. So here, this polynomial right here is a bunch of terms added and subtracted together. So if I want to take the derivative of the whole thing, I can take the derivative of each one of these parts separately because they're added and subtracted together. So I'm going to do that. So f prime is going to be the derivative of x cubed plus 2x squared minus 5x plus 1. I'm writing this out. I'm writing way more than I need to write here, but that's just sort of to get you used to the idea of how these rules are going to be applied. And so since these are added and subtracted together, so I'm going to be able to take the derivative of x cubed separate from the derivative of 2x squared, separate from the derivative of 5x, separate from the derivative of 1. Now looking at this one and this one each have a constant multiple in them. Here I just have x to a power, and here I just have a constant. I can take care of those using the respective rules. But here I'm going to say, all right, well I have the derivative of x cubed plus 2 times the derivative of x squared. That constant multiple can get pulled out, minus 5 times the derivative of x plus the derivative of 1. All right. So I applied the sum and difference rule. Then for these two, I applied the constant multiple rule. Now looking at what I have, derivative of just x to a power, x to a power, x to a power, and a constant. So if I apply the power rule to the first three and a constant rule to the last one, not constant multiple, but just the derivative of a constant to this one, you can see that I'm going to get 3x squared plus 2 times 2x minus 5 times 1 plus 0. Those are these respective derivatives. And so I end up with 3x squared plus 4x minus 5. So the derivative of f prime is this. Now my goal for you is to ultimately have you look at this and just automatically tell me that this is the derivative. That may take more time for some of you than others, but hopefully by the end of this homework, you would definitely be able to jump from there to there. And that's going to be vital to working in the next couple of sections, and really for the rest of the semester, that you're going to have to be able to take the derivative of polynomials much quicker than what we just did. I did all this so that you see exactly which rule we're applying and how it applies to this problem. Okay, so let's go to the next one. I got to erase, make some room. All right, let's clear this out, clear this out. All right, look at the next one. The next one, we also have a sum or difference. So we have terms added and subtracted together. If you look at g of x, if I want to take g prime, what I'm going to do is I'm going to take the derivative of the whole thing, but that's going to then allow me to take the derivative of negative x to the 5th over 3, separate from the derivative of 3x squared, separate from the derivative of 1. Why? Because of the operation, addition and subtraction. Then the negative 1/3 here is going to come out, and I'm really just going to take the derivative of x to the 5th, plus this 3 is going to come out as a constant multiple, times the derivative of x squared, minus the derivative of 1. And so looking at this, I have negative 1/3 times the derivative of x to the 5th, which would be 5x to the 4th, plus 3, and they're multiplied, plus 3 times the derivative of x squared, which is 2x, minus the derivative of 1 is 0. So I end up with negative 5/3 x to the 4th plus 6x. There's my derivative. This is a 4. Okay, so polynomial derivatives should be really pretty easy. And with practice, you'll find that that is the case. But it takes practice. Okay, so let's go with one more example. All right, so let's pick a color. Let's say we got y equals 4x cubed plus 5x squared plus 6x minus 1. So this is the function I want to take the derivative of. So y prime, if you think about it, should allow me to take the derivative of this, separate from this, separate from this, separate from this. Why? Because they're added and subtracted from one another. Now, if I go to take the derivative of this piece, this 4 is a constant multiple, which would come out. I'd take the derivative of the x cubed, which would be 3x squared, plus this 5 is a constant multiple, which would come out, and the derivative of x squared is 2x, plus 6 is a constant multiple, which would come out, and the derivative of x is 1, minus the derivative of negative 1, which would just be 0. So I end up with 12x squared plus 10x plus 6. There's your derivative of this function. So definitely practice. More practice you have, the better you get, and that'll help you while we move through and learn more rules. Product rule, quotient rule will be the next ones up.